This video is really short and just talks about recognizing the perfect square trinomial factor pattern and making sure that we understand what a perfect square trinomial is. Remember that a perfect square trinomial is the product of a binomial being squared. So when I have a binomial multiplied to itself, I get this pattern, a squared plus 2ab plus b squared. That's because I'm going to square the first term and square the last term, which is pretty clear when you're foiling something, right? The firsts in this example right here would be 4x squared. And the reason why that happens is because I'm taking 2x and multiplying it to itself, right? Or squaring 2x. The lasts ends up being 3y squared. Again, that makes perfect sense because I take 3y and multiply it to itself. But we always have a middle term. In this particular case, that's the outsides and the insides, which would end up being the exact same product. Both of those are 2x times 3y. So I'm going to have 2 of the product 2x times 3y. And that's where this 2ab comes from. 2 of the product of the insides and the outsides, or 2 of the product of the terms that are in that binomial being squared. If you recognize this pattern, things become so much easier for you. And all it is just recognizing your perfect squares. If I look at this first example, I have x squared plus 10x plus 25. And immediately I notice that x squared is a perfect square and 25 is a perfect square. So now it's about testing it out to see if it's a perfect square trinomial. The way that I do that is I ask myself a couple of questions. Is the first term a perfect square? I've already identified that that's yes. If it is, I'll take the square root of it to figure out what was the thing that was being multiplied to itself to create it. The square root of x squared is just x. Is the last term a perfect square? Again, the answer is yes here. And the square root of 25 is 5. That's what was multiplied to get it. Now I need to test out this middle term. Remember, the middle term is the product of the two terms that were part of the binomial being squared. Is x times 5 times 2 10x? That is true, right? Because remember, this would be 2ab. Well, the x is like a and the 5 is like b. Since that is true, I know that I have a perfect square trinomial. That allows me to put parentheses on it, put a square, and then decide what sign has to go here. In order for it to be a true perfect square trinomial, the constant term must be positive, has to be positive. The sign on the binomial follows the sign of the middle term. So if it was a negative 10x, that would be x minus 5. Since it's a positive 10x, it's x plus 5, quantity squared. You could also write this expanded if you want, and you can write x plus 5 times x plus 5. Let's test out this one. 16x squared minus 24xy plus 9y squared. 16x squared is a perfect square. The square root of that is 4x. 9y squared is a perfect square. The square root of that is 3y. Now I need to test to see if that middle term is the product times 2, or 2 times the product of those square roots. 2 times 4x times 3y is 24xy. That's true. So now I just need to make sure that the last term was positive. It is. And then the sign on my binomial follows the sign of the middle term. So in this particular case, it was going to be a negative. For all of these, you want to make sure they're in descending order. Otherwise, you can't really tell whether you have a perfect square trinomial. Let's look at the last one. 49z squared minus 20z plus 4. 49 is a perfect square. That's going to be 7z. 4 is a perfect square. That's going to be 2. And now I need to test to see that the middle is 2 times the product of those square roots. 7z times 2 is 14z, and 14z times 2 is 28z. That is not a perfect square trinomial. So then I would try and factor that like normal, which we haven't actually talked about yet. This one actually ends up not being factorable, so you would just write prime. This is a bonus slide. You really can stop here if you want, but if you wanted another method of factoring, sometimes this works pretty well for helping you find the factors that you need to create something, the middle term. And so this method is called factor by grouping. When you have a trinomial and your leading coefficient is not 1, something that you can do in order to find the factor pairs pretty quickly on what needs to create it is find all the factors of the first and last term like you normally do. And then find the product of those first and last term. What this does is it gets all of these factors together into one number, and so that would be 30. And then I'm going to find the factors of 30. That'd be 1 and 30, 2 and 15, 3 and 10, 5 and 6. I'm back at 6, so I found them all. Then you select the set from this that can create the middle term. In this case, I'm looking to create a 7, and 3 and 10 are the only ones that I can create there. In order to make that 7 negative, it would have had to have been a negative 10 and a positive 3. What this allows me to do is it allows me to see what the outside and inside terms were in order to make this product, and it helps me to go just a little bit faster. And so I know that because 5x squared only has one set of factors, I'm going to go ahead and put those in, 1x and 5x. And I need to make a 10 and a 3. Well, there's only, if I'm looking here, there's only one thing that 5 can multiply by to get a 10, and that would be a 2. So I know that the 2 had to have gone here to create my 10x, which means the other factor pair is that 3, and that one had to have gone there. And 3 times 1x is 3x. It just kind of helps you go a little bit faster. Now I know that it was a negative 7, so that had to have been negative 10 and positive 3. And it would be a negative 2 to make that a negative 10 product, and positive 3 to make that a positive 3 product. It's just a method of helping you go just a little bit faster to find those factor sets. Sometimes what I do is I ignore the fact that 5x squared times negative 6 is 30x because I know that the x's had to go here. So these actually would have x's on them, but I just don't do that. I don't bother with that.